Hello, everyone. I'd like to thank you for attending this technical webinar. Our webinar today is titled Optimizing the LiDAR Signal Chain, Sensors and Integrated Processing Solutions from Semiconductor and LeddarTech. My name is Baman Haji from Semiconductor, and I'll be moderating the webinar. So with that, I'd like to start by talking to you about LiDAR. As many of you are familiar, LiDAR is a crowded ecosystem with many architecture decisions. And what the two organizations that are hosting this webinar are doing today is forming a strategic collaboration to improve the time to market and reduce the overall cost of LiDAR systems. We're doing this by combining Semiconductor's leading edge sensors with LeddarTech's Readout solutions in complete reference designs, targeting LiDAR module manufacturers, system integrators, and automotive tier ones. So what we'll be showing you today is a 16-channel LiDAR reference design that was jointly developed with a full application note, and it will serve as a comprehensive development platform on which these customers can build. So we'll provide an introduction to the architecture of LiDAR and details of the reference design. So what we'll learn in the next hour are what Semiconductor's silicon photomultiplier sensors do for LiDAR in enabling high performance and long range. Due to the unique fast output mode, their low operating voltage and high internal gain. We'll also learn about the different types of readout solutions that are possible for LiDAR after the output of the sensor. You can use analog to digital converter based full waveform processing or time to digital converter based readout. LeddarTech will go through the LCA3 system on a chip, which is an integrated readout solution with full waveform digitization. And then we'll go through the details of the silicon photomultiplier and LCA3 ADC-based reference design. And the key takeaway that you'll see is that we're able to increase the dynamic range performance of a LiDAR by more than 5 times, and to reduce the cost of the LiDAR system by 70% per channel by going to this integrated solution that uses a silicon photomultiplier with an ADC-based readout. So that's our agenda for the next hour. Again, we'll have an introduction to LiDAR architectures and different depth sensing methodologies, and then talk about the reference design. I'm joined by my colleague, Aidan Brown, who's an applications engineer from our automotive sensing division. I'm responsible for business development. And from the LeddarTech side, we have Heinz Eurer, who's the director of strategic partnerships, and Rainer Stahlberger, who's the manager for platform architecture and signal processing. And last item for the audience here is, if you have questions throughout the presentation, please type them into the chat box, and we will get to them at the end. And if you're having any issues with Demio, please make sure that your firewalls and ad blocking services are disabled. So first, a little bit about Semiconductor. We're a global company with a 34,000 employee workforce that was originally a spinoff of Motorola in the year 1999 and went public in the year 2000. We've grown organically and through acquisitions. And Aidan and I are part of the team that came through with the acquisition of Sensol Technologies in 2018, specializing in silicon photomultipliers and single photon avalanche diode detectors used in LiDAR and medical imaging applications. We are part of the intelligent sensing group. So Semiconductor has solutions for LiDAR in addition to radar and CMOS image sensors for cameras. And across our broader business groups with our Power Solutions Group and Advanced Solutions Group, Automotive represents 34% of the revenue of the company globally. And with that, I'd like to hand over to Heinz to talk about LeddarTech briefly before we get into the meat of the presentation.
So thanks, Bauman. Let me tell you a little bit about LeddarTech. LeddarTech is a leader in environmental sensing solutions for autonomous vehicles and advanced driver systems. And LeddarTech has 14 generations of solid-state LiDARs based on the LiDAR LaddarEngine platform, which are operating 24/7 in harsh environments. More than 50,000 units have been sold, representing a total of more than 40 million hours of operation. The platform is actively deployed in autonomous shuttle, truck, bus, delivery vehicles, smart city, factory, and robotaxi applications. But LeddarTech also enables the development of automotive-grade solid-state LiDARs based on the foundation of the LaddarEngine platform. LeddarTech's mission is to drive the ADAS AD LiDAR market with an open sensing platform, enabling Tier 1 and AD system integrators to design their own differentiated LiDAR solution. It is an open platform enabling all ADAS and AD applications from L2 to L5. It is a versatile, scalable, cost performance, optimal automotive-grade LiDAR solution. And as you can see here, first we have the software and the data, which comes with signal processing, which is something that we focused on very early and what LeddarTech was originally founded to develop. This technology, now with over a decade of refinements, is embedded in all of our products. Today, it is the only complete signal processing library for automotive LiDAR, and it can multiply the performance and range of most LiDARs. Now moving to hardware components, we have our LiDAR system on chip, or SoCs. They are the only LiDAR SoCs designed specifically for AD and ADAS. And these SoCs enable a massive reduction in cost, size, and power consumption, while accelerating the time to market and importantly, providing a solution that is designed for functional safety from the ground up. And finally, we have an area of reference designs that can meet the industrial's price and volume requirements right away. These reference designs are backed by our ecosystem partners like onsemi and fully supported by our application engineering team, allowing our customers to customize while starting from a proven software and hardware platform, minimizing risk and accelerating the time to market. So today's webinar is about such a reference design, and now let's look deeper into such a 16-channel LiDAR reference design.
Thank you, Heinz. So next I will go through the depth sensing methodologies and specifically direct LiDAR. So LiDAR is a method to measure distance using active illumination. There are other ways to do depth sensing. You may be familiar with using stereoscopic vision or multiple cameras to measure distance. This is similar to the way our eyes work, where you use the disparity between the view of one camera versus the other to measure the distance to an object. But for high resolution, high accuracy depth sensing using direct time of flight LiDAR, where you send a short laser pulse and you start a timer and you have a sensor that will then look for photons of that same wavelength coming back, and you use the speed of light to measure it, that's the most accurate way to measure distance. The benefits that you have from using depth sensing with LiDAR versus other technologies like radar or ultrasonic are the depth resolution and the ranging distance. So for example, with a radar system, you are able to range to long distances, but you only get a certain few number of points across your scene, whereas with LiDAR, you can get a full view of the surroundings. Now, in a direct time of flight LiDAR system, you have 6 major hardware functions. You have the transmit, the receive, the beam steering, the optics, the readout, and the power and system functions, as shown in the block diagram on the right. So I described to you a single point LiDAR. The reason that you need the optics and the beam steering is to then scan across and get a view of the entire scene. On Semiconductor, we have components for all of the blocks that you see shaded in green. So we do not have components for the illumination or for the optics and beam steering. And our partners also have solutions for the readout, like you see what we're doing with LeddarTech today. And our goal is to offer system solutions for LiDAR where we bring all of the pieces together and enable our customers to build on that so they're not having to build it from the ground up using individual single components. In automotive LiDAR, we've been able to be very successful with our near-infrared, red-sensitive silicon photomultiplier detectors and spat arrays. We have multiple design wins, and we've really developed this technology since the early days of Sensel 15 years ago to provide the lowest noise, highest performance, and best uniformity. And we have a host of evaluation boards and reference design and kits, one of which will be, or two of which we'll be talking about today. So what we've done to enable the LiDAR ecosystem to use our sensors is initially, as you'll see talked about by Aidan, we had to show that you could use these high-performance single-photon sensitive silicon photomultiplier sensors in LiDAR. And we started with single-point demonstration systems that you see in the bottom left part of the slide. Then we expanded on those capabilities by going to 3D scanning systems built on both our silicon photomultipliers and our spat arrays. And these were also demonstration systems that would be used at trade shows and to show the performance of our sensors in a LiDAR. And what we started to do more and more after showing the capabilities is to build these reference designs which would be able to be leveraged by customers. And that's what you see in what we call phase 3. And what that all builds up to is this ecosystem of partners that we've brought together in our LiDAR Partners program. This is a combination of LiDAR module manufacturers, in addition to LiDAR component suppliers that we promote products with to be able to get our customers to get to market faster. And that allows them to skip the time that would be normally be spent in the pre-study or proof of concept period, because they're either able to receive an already working LiDAR module, or they're able to build on a reference design and make their own module. So with that, I'd like to hand it over to my colleague Aidan Brown, who will go through the technical background of direct time-of-flight LiDAR sensors and the reference design.
Thanks, Bauman. So there are several different types of detectors for direct time-of-flight LiDAR. Legacy detectors such as pin diodes and avalanche photodiodes, or APDs arrays, are fast being replaced by more sensitive detectors such as SiPMs, SiPM arrays, and spat arrays. Some of the pain points for pin diodes are the very low gain, and for APDs, it's the high voltage and poor uniformity. Because of the low to moderate gain of these legacy sensors, they require higher amplification externally, which leads to higher amplification noise. SiPMs, SiPM arrays, and spat arrays operate in Geiger mode, where they benefit from single photon resolution and have very high internal gain, up to a gain of 1 million on chip. These are all manufactured in a CMOS process, where we have excellent uniformity by design and have low operating voltages, typically from 20 to 50 volts. So we're seeing that SPAD and SiPM devices are being increasingly adopted for LiDAR over legacy sensors, such due to their low cost, manufacturability, and performance advantages. So how does an SiPM or SPAD sensor operate? So the basic building block is the SPAD. It's got 2 pins, a cathode and anode, and a quench resistor. So a SPAD is operated above its reverse bias voltage in what we call it, where it operates in Geiger mode and benefits from very high internal gain. On receipt of photons, it produces a measure of current, which is burnt across the quench resistor during its avalanche phase. It then resets and charges back up from its breakdown voltage to its applied bias voltage. So a SPAD or microcell can be used to time or count single photons. An SiPM, or silicon photomultiplier, is an array of SPADs where each SPAD is connected together in parallel. Again, we have 2 pins, a cathode and an anode, but this time we can provide proportional information. So if one microcell or SPAD triggers, it produces, again, the same measure of charge. If 2 microcells trigger, they produce twice that measure of charge. On the bottom left-hand side here, we show a schematic diagram of an SiPM. And on the right-hand side, we can see an example of one of our discrete micro-RB SiPM sensors, which has about just under 1,600 SPAD microcells within its active area. Unique to on semiconductor SiPMs is the fast output. So this is a capacitively coupled output connected to each of the microcells or SPADs. And it produces a narrow voltage pulse where the amplitude of the pulse is proportional to the number of microcells that have triggered. The pulse width is generally on the order of around 1 nanosecond. And due to this narrow pulse width and not being constrained by the recovery time of the standard output, it can be used to measure higher photon count rates. The fast output is AC coupled, and so it doesn't carry any DC information. If you were switching to an SiPM from another legacy detector, such as an APD, there are some system-level optimizations that you should be aware of. So SiPMs are highly sensitive and have fast recovery times. Thanks to this, they can be used with very short sub-nanosecond laser pulses. This enables high peak power pulses to be used while maintaining eye safety. APDs generally need large apertures to capture the light due to their low internal gain. SiPMs are much more sensitive and can be used with smaller optical apertures for lower cost and cleaner integration into a system. In terms of the readout, SiPMs, as we discussed earlier, have a higher internal gain, 10K times more than an APD and 1,000,000 times more than a PIN diode. So the feedback resistor value can be reduced while still maintaining good signal amplitude. On the type of amplifiers used, a higher bandwidth amplifier would be required to preserve the fast rising edges of the SiPM signals. But lower bandwidth amplifiers can be used, but may not offer optimal performance. So there are some critical sensor requirements for automotive LiDAR. The first is the sensitivity, and the sensitivity at 905 nanometer. And sensitivity for an SiPM is spec'd by the parameter PDE, which stands for photon detection efficiency. Today, 18% is the best in class for the near infrared. And we see that the near infrared wavelengths will be the dominant wavelengths for LiDAR due to the 10 times lower cost and large ecosystem available. The next is the gain and signal to noise ratio. SiPMs have much more gain internally than other legacy detectors. This combined with the high PDE, low crosstalk, and dark noise offer excellent signal to noise ratio. Tight uniformity by design. So SiPM sensors, thanks to being manufactured in a CMOS process, can offer tight uniformity of the voltage and gain across millions of sensors. This reduces the need for system calibration and helps to lower the manufacturing cost. And the last one is automotive qualification. On Semiconductor has brought the first automotive qualified SiPMs to market. These are manufactured to IATF 16949 and follow AEC Q102 stress-based testing and operate from -40 degrees up to 105 degrees. An example of an automotive qualified SiPM array is our 1x16 SiPM array. This is a monolithic SiPM array, which offers the best in class PDE and noise performance thanks to the utilization of microlens technology. On the left-hand side here, we have some of the parameters describing this array. So we have 368 microcells per pixel, and each microcell within the pixel is 10 micron by 10 microns, again, utilizing that microlens technology. On the right-hand side here, we have an image of the actual array and a schematic, its internal schematic. So we can see that there's a common anode, and we can connect to the individual standard outputs or the individual fast outputs for each pixel. So the advantages of an SiPM array such as this includes the single photon sensitivity, and also highly uniform pixels biased with a single supply. And now we can acquire 16 depth points simultaneously with this one array. So I'd like to talk to you about our LiDAR reference designs. So using this 16-channel SiPM array, we can now offer you both TDC and ADC-based readout architectures. So these reference designs are using our 16-channel SiPM utilized for scanning LiDAR applications. So these reference designs contain all the electronic functionality for driving the laser pulses, detecting the return signals, and generating the point clouds. Just to note that the system optics, scanning, and motor control are outside the scope of these reference designs. So I get just focusing in on the TDC-based architecture. So in this block diagram, we can see that the time to digital converter, or TDC start signal, is generated by the outgoing laser pulse. The laser pulse hits the target and gets reflected back to the SiPM sensor. This produces a signal which is amplified and then compared to a set voltage threshold. The output of the comparator provides the stop signal to the TDC. The photon arrival is timestamped by the TDC and histogrammed multiple times. The peak of the histogram then becomes the depths to the target. Using this method, we can increase the signal to noise ratio further of the SiPM sensor. This is our 16-channel TDC-based reference design, and that's available now from on Semiconductor. It contains a detailed application note and all the design files, bill of materials, and FPGA code. And the application note includes a full description of the design, implementation advice, and hardware test results. So just to note that this reference design is a development platform. It's not a complete LiDAR system, so it doesn't include the optics, motor control, or beam steering. But it does contain all the design files for the SiPM readout, FPGA code, and power supply and laser driver. I was going to pass you over to Rainer now, who's going to talk about the ADC-based architecture with integrated processing.
Thank you, Ian. I would like to give you in the next minutes an overview about the LeddarTech technology, which is based on the full waveform processing based on an ADC architecture compared to the TDC architecture explained from Aiden before. First of all, I would like to give you also an overview about our highly integrated solution, means the LCA3 ASIC, figuring out the advantages of the integrated solution, and then giving a little bit more details about what we mean with raw waveform full processing. So on the left side here, you see at the end a 64-channel discrete system. Discrete system means we have here discrete components like the TIAs, the transimpedance amplifiers, also discrete external multiplexers, and also discrete ADCs. And what you can see here, that for this discrete solution, approximately a size of in the range of 12 by 12 centimeters is necessary. And what we can do with our highly integrated solution with the LCA3, we can shrink this and something in addition, to a solution only by 12 by 12 millimeters. And this gives, first of all, significant improvements for this integrated solution, and also as a key enabler for automotive solutions, where first of all the form factor is significantly important, and secondly also for sure always the cost. And starting with the form factor, so with inside the LCA3, we were able to integrate up to 64 photodetector inputs, which are then internally multiplexed to 16 complete parallel processing channels. Processing channels complete means we have integrated for all 16 channels the transimpedance amplifiers, then necessary analog filters, plus the ADCs for all 16 channels, and then also some post-processing. But this is not everything. Yeah, we also have integrated, and this is a huge also advantage for a LiDAR solution, a freely programmable LiDAR sequencer, which is able to control not only the lasers, which is also able to control or to be controlled with the MEMS mirror solution. So it's not only the capturing unit, there's also sequencing stuff included. And when we compare now the channel costs, yeah, for a discrete solution compared to when you integrate it or you use a highly integrated solution, we are able to reduce the overall cost per channel by up to 70%. And not only from this integration point of view, also, as Heinz also mentioned in the intro, because also the ASIC is developed according to compliant up to ASIL B, which also reduces then the development cost for our customers in terms of function and safety. And from layout complexity, due to the use of only standardized digital interfaces and due to the use also of a standardized package, it's easy at the end also to make a mass production with the ASIC, which is also a prerequisite, let's say, for the automotive solutions. Now some words to what do we mean with full waveform processing. So on this slide, we would like to figure out, first of all, a typical scenario or what can happen in the field. Yeah. So first of all, and which are the resulting, let's say, signals what we capture then at the end on the photodetector. Yeah. So for example, we have a very close reflection from the cover glass. Then, for example, environment conditions like fog, which gives also a dedicated signature. Then the targets like, for example, the tree, the pedestrian or the house, and also some additional ambient imperfection coming, for example, from the ambient light. And when you combine now all these artifacts, you get then on the lower side, the complete raw full waveform. And this is now really, this complete raw full waveform, this is what we completely capture now with the ADC. Yeah. And then after some pre-processing, we see a much clearer picture of the waveforms which are now in these detections. Yeah, and out of these waveforms, we can then now extract this imperfection. For example, we can then extract out of it. It seems there was fog in the view, or for example, to distinguish between this low reflective target like the pedestrian and the high reflective target like the house. Yeah, out of these shapes, we are then possible to reconstruct what was really in the field of view. Yeah, and that's why this we also see definitely as a significant improvement. Yeah, because we can compensate with the full waveform processing also for imperfections, what will always be in any kind. In any field of view, what you will get. Summarized, what we see as the benefits using the full waveform processing and the ADC architectures is that it allows us, yeah, compared to the TDC architecture, only with one single shot, yeah, to get at the end multiple detections on per trace, yeah, which at the end also reduces dramatically also the overall power consumption because less laser shoots for detection are necessary. With the full waveform processing, we are able to detect imperfections, yeah, coming, for example, from fog, environment conditions, or also, and very prominent, from crosstalk, yeah, crosstalk optical or electrical. Yeah, and with let's say proper characterization, we are able to compensate on a system context also on the full waveform for the crosstalk, which also gives us the possibility to detect weak targets which are superimposed by crosstalk, and also not only in detection, yeah, also in terms of we can correct on the distance error. What also we can improve for the following perception. Yeah, we get a very huge dynamic range with this approach here, more than 100 dB, which gives more detailed information than also for the perception to optimize at the end the classification of the objects. And at least, yeah, with this flexibility, it supports also to use not only one photodetector technology, also several. So we are compatible with PIN APDs, and what we will also demonstrate in this webinar or in this project with an SiPM. And it gives us, due to the fact that we have this full waveform processing, we are not treasure holding in the analog domain like for the TDC approach. We are treasure holding if it was a detection in the digital domain, and this gives us additional, let's say, flexibility in, let's say, adjusting to dedicated or different LiDAR environment systems. Now a few words about the LCA3 eval board, what we also used for this project, to demonstrate the powerful combination with the onsemi SiPMs. So the LCA3 eval board is not only the ASIC standalone, it consists of several connectors and enables at the end our customers to very easily build a complete LiDAR system around our eval board. Means you can easily connect any kind of, let's say, a laser or let's say transmitter unit on this. You can connect a MEMS unit on it, and you can connect also via dedicated connectors and photodetector SiPM or APD on this eval board. And this is what we did now on this project. In addition, to complete, let's say, the full portfolio of LeddarTech, we are also possible to connect an additional microcontroller to our eval board, where we are then able to run our LiDAR signal processing software, which then makes out of the detections really the point cloud. And in addition, we also provide software for visualization, easy to showcase at the end then the detections. And a few words again also on what does LaddarEngine means in a LiDAR context. LaddarEngine means it is our ASIC, it's the LCA3, plus the signal processing software, but the signal processing software is not only placed in microcontroller, it's split a little bit between FPGA and signal processing, plus additionally features regarding functional safety, regarding additional features regarding sequencing in a complete system context, at the end really to be the core of a LiDAR system, which can be adjusted to any kind of a surrounding LiDAR system architecture, if it's then an SiPM for our project here, or different beam steering activities. And this at the end is then a key enabler for an easy and fast LiDAR reference design. Then I would like to hand over again to Aidan to go into more details about, let's say, our reference design.
Thanks, Rainer. So this is the block diagram of our combined reference design. It contains our on-semiconductor SiPM array PCB. So this PCB contains our 1x16 SiPM array, a lens mount, a board-to-board connector that's compatible with the LCA3 eval board. We also have a power PCB, which provides the boost power supply for the SiPM array, and for our laser PCB, which provides the illumination source.
Yeah, on the LCA.
Sorry, Rainer, go ahead.
LCA3 eval board. Thank you. Sorry. On the LCA3 eval board, we have, as said before, we have the LCA3 ASIC, which an additional clock generator. Then we have a CSI2 bridge. As I said before, parts of our signal processing are placed not only in pure software, also supported by an FPGA. That's why we have this CSI2 bridge with the connection then to the signal processing in the FPGA. And we also have then to make, let's say, to ensure the compatibility between the onsemi boards and the LeddarTech boards, we also have to develop an interface board, which is simple, really a converter at the end from the connector from the eval board to the connector of the onsemi PCB board.
And here we have the physical boards. So here we can see the LCA3 eval board. And here's the on-semiconductor SiPM array PCB. So we have our lens mount. This is the SiPM array right here. And we have some series resistors connecting the fast outputs to the input of the LCA3 through some board-to-board connectors. And we have some options for a bench power supply, our connections to our power PCB. And here's our laser PCB, and as Rainer described, the LeddarTech interface PCB to connect from the LCA3 to all of these different boards. So I'm going to pass back to Rainer just to talk about the simulation setup and results.
Yeah. So before we started with the project in hardware, for sure, we did a lot of simulations to really check, okay, is it physically possible to combine the onsemi SiPM with an LCA3? And we started to evaluate both options from the onsemi SiPM. So first of all, the standard output, and then also the fast output. And because on the fast output, we had our concerns regarding this extremely slow pulse, what we get if we would be able, with the sampling frequency of the LCA3 ADC, if we can capture it. Yeah, but at the end, it figured out, yeah, that with a proper, let's say, usability of the LCA3, so we used then the LCA3, as you can see here on the left upper part, yeah, the internal peer only as an inverting amplifier, and with a proper choice of this external resistor R1, we were able not only to level at the end the input dynamic to make it compatible with an LCA3, we were also able, especially with the only with the fast output is this possibility with the internal AC coupling capacitance, also to broaden the pulse, yeah, and then at the end really to make it, let's say, very suitable to be captured with an LCA3. And summarized, yeah, as I said, it figured out that the fast output is the much better choice in combination with an LCA3, not only technically, because also from cost perspective, because only one external component is necessary to combine these two options. And at the end, it was the better choice also to increase the pulse width to get at the end the possibility to sample it with the internal ADC sampling frequency.
So then we built up the physical boards, and we made several measurements. On the left-hand side here, we made a reference measurement by connecting the output of the SiPM array PCB through that 1 kilo ohm resistor on the fast output through an amplifier to an oscilloscope as our reference. And this is the output of the LCA3. And we can see that we can recreate the output, the fast output pulse with the LCA3 through digitization. And now what we also did was looked at the single photon pulse height. This was a measurement done in the dark. So we looked at the single photon response from the dark noise of the SiPM. And we compared that for two different gain settings, from a gain of 64K and a gain of 2K on the TIA front end. The gain of 2K, as per the simulations, offers the best dynamic range. And we compared all those measurements to our current TDC-based reference design. So we can see that the single photon height we just measured here in TDC in ADC codes. You get about 250 ADC codes for the gain of 64K, and about 170 for the gain of 2K. And on our TDC-based reference design, it's slightly different. It's about 33 millivolts. If we look at the single photon pulse width for the ADC-based reference design, is between 9 and 8 nanoseconds. It is much shorter on the TDC-based reference design. We're at 1.5 nanoseconds on the pulse width. But I think the key takeaway here is the significant increase in dynamic range when using the ADC-based approach. So we have a significantly improved dynamic range. It's nearly 5 times improved when using the 2K gain setting in the ADC-based approach compared to our TDC-based board. One thing to note here is that we used a development sample of the 1x16 SiPM array for these measurements. So the gain and the bias voltage are lower on the production intent device. So we will be remeasuring this and updating our application note in the future. But there are more details on this testing captured in the application note, which will be available to you at the end of this webinar. So now I was going to pass you back to Bauman for the conclusions.
Thanks everybody for listening today. To show you how we've combined on Semiconductor's technology along with LeddarTech's technology to show a high performance LiDAR reference design. We use the best in class silicon photomultiplier sensor with the maximum photon detection efficiency achievable on the market to get long range LiDAR, along with the full waveform processing that LeddarTech's technology offers to increase the dynamic range of the LiDAR system by more than 5 times. And as Aidan referred to, this is really the difference between being able to see a low reflectivity object versus a long reflectivity object at a distance. from a very small pulse that may come back reflected from a low reflectivity object. And the integrated solution gives the lowest cost per channel. So what you'll be able to do now, if you look at the handouts tab on the right, is download the reference design application note to go through a detailed overview of what we talked about in the presentation today and the test data. And you can also contact on Semiconductor and LeddarTech in the email addresses in the application note to get access to the reference design and the LCA3 evaluation hardware. So we'd like to thank you for listening. I see that we have about 20 questions that came in, so I'm going to go through some of those questions. I will answer some of them, and I'll yield to my colleagues for some of the other ones. So I'll get started with those, and we'll try to get through all of the questions in the remaining 18 minutes that we have today. So the first question, I think this one can be for you, Aidan. Can you talk more about the benefits of SiPMs versus other types of sensors that you mentioned, like avalanche photodiodes and pin diodes, with respect to system integration into a LiDAR?
Sure. So I guess with SiPMs, everything's manufactured in CMOS, so we can offer better uniformity in terms of our breakdown voltage and in terms of the gain of the sensors. This removes the need for any calibration. It also reduces the manufacturing cost. Our sensors are manufactured within the manufactured in silicon, so it's a CMOS process. They're within the quantum efficiency of silicon, so they are near infrared detectors, primarily focused on 905 nanometer or 940 nanometer, but do work at other wavelengths, between 200 nanometer to say 940 nanometer as well. So the near infrared has a higher, or a very large ecosystem of lasers and other ecosystem components available that can be integrated into a LiDAR system. Compared to, say, APDs or pin diodes, the biggest selling point is the high internal gain. So with the APDs and pin diodes, you need to have a very high external gain. That leads to higher amplification noise. So that can be mitigated using an SiPM due to the very high gain on chip.
Thanks, Aidan. I think the one other thing I'd add is with respect to the optics, the sensitivity of the SiPMs means that you can use smaller optics and lenses for cleaner integration into the LiDAR modules that might go into the vehicles. That's
correct. So SiPMs can be used with a narrower angle of view, smaller apertures, so you don't need as large a hole in the system. So it can also be used to enable smaller, more compact LiDAR systems.
Okay. I think since we just answered that one, I'll jump to another one that's related that you touched on. In terms of operation frequency, is there any difference for each LiDAR system? So this is a topic that we covered in a longer talk that's available on the OnSemi website under LiDAR talks called the Great Wavelength Debate. So the silicon photomultipliers that we use operate in the near-infrared wavelengths, as Aidan mentioned, up to about 1,000 nanometers. There are also LiDAR systems that operate in shortwave infrared, for example, 1550 nanometers, but those require the use of more exotic semiconductors like indium gallium arsenide for the sensors, and also for the lasers, they have to use smaller wafer size foundries because they have to alloy the gallium arsenide lasers with indium phosphide. And what that ends up in is a higher cost system, and the ecosystem availability of the components is not as large. So I encourage you to reach out and view that longer talk on this topic. Next question, I think for Rainer. In designing the LCA3 to work with multiple sensor types, so you showed on the slide that it works with SiPMs, but also APDs and pin diodes. Are there any design benefits or trade-offs for the SoC for using an SiPM sensor with a large gain and very fast pulse response?
Yeah, so the main advantage, yeah, what I definitely from the electrical point of view, what I see is definitely that most of the, let's say, gain is done in the SiPM itself, yeah, which relaxes at the end then the requirements for the overall noise figure for the ASIC significantly. This is a huge benefit, I would say, compared to the SiPMs. Yeah, what we also see is that the benefit that the input dynamic range from an APD is extremely huge. Yeah? So we're talking here about, let's say, a nanoampere up to let's say a few hundred milliampere. And for the SiPM, yeah, it's very good calculate-able because it depends on the number of SPADs on an SiPM pixel. So it gives a better, let's say, a specification or a requirement, a more clear requirement based on the technology itself, and it's less independent than finally on the system architecture. And this is at the end then definitely much easier at the end to fulfill for building an ASIC. For sure, what has to be, let's say, what we have to handle carefully with SiPMs, especially with the fast output, is that the sampling frequency inside the ASIC fits to be able to capture at the end the pulse, but especially with the fast output, yeah, in combination with our circuitry, we were able to figure out, okay, we can definitely enhance it, yeah, and that's why at the end I would say we can get the best of both worlds.
Thank you, Rainer. Next, I'll also go to a related question on the topic we just touched on. Any eye safety issues with 905 nanometer laser? This is a common question. Of course, one of the differences between 905 nanometer and 1550 nanometer is that you can output more laser power at the shortwave infrared wavelengths due to the fact that it's absorbed in the eye before it hits the retina. But the short answer to this is that there are eye safety specifications. So at 905 nanometer, you have to stay below the eye-safe laser power. And so the systems that are built by LiDAR module manufacturers, the reference designs and demonstrators that we make, they all operate within the eye-safe limitations. And so when we talk about ranging of 250 meters in outdoor bright sunlight conditions with 100,000 lux, we're talking about using an eye-safe laser power. So as long as the system is designed properly, there are no eye safety issues. Next one, back to a technical question for Rainer. Can you elaborate a bit about the physical sampling rate of ADCs in the LCA3, particularly as we're talking about nanoseconds of pulse width on the SiPM response?
Definitely. So currently the LCA3 design is figured out, or the requirement for ACs we are sampling internally with 320 megahertz. That's why at the end it is necessary to increase the pulse width in the range of approximately 10 nanoseconds to have a few samples per trace, and then internally in our signal processing chain we are then possible to interpolate at the end then within this detected pulse to then get a very good accuracies in terms of distance and also in terms of precision.
Thank you, Rainer. Next, I will, let's see, questions are still coming in. Okay, is it possible to extract the information about the reflectivity of the target from the sensor data? So as Aidan explained, this depends on the sensor type that you use, but with a silicon photomultiplier, and the advantage is that you have an array of SPADs, single photon avalanche diodes. And so your pulse output is going to correlate to how many of the SPADs fired, so how many photons you detected. And based on that, you can sense the reflectivity of the target and not just the time of flight distance. So in the example that we showed in the reference design, when we use the TDC-based readout with the silicon photomultiplier, you can see distinctly 73 different photoelectron levels and with respect to your dynamic range for reflectivity. And this is much more difficult to do if you have a sensor that is integrating like a PIN diode or an avalanche photodiode, which doesn't have as much gain and needs to integrate the signal as it comes out. Okay, next let's go to any reason why the input stage of the LCA3 is a transimpedance amplifier and not a voltage amplifier. I assume voltage amplifier is more suitable for an SiPM. Rainer and Aidan, I'll let you guys take this one.
Yeah, maybe I can start, Rainer. So I guess,
okay, go ahead.
If we were using the standard output of the SiPM, you could still use a transimpedance amplifier. It's similar to an APD. It produces a photocurrent, and we can convert that photocurrent to a voltage using a TIA. But you would have to reduce the feedback resistor because of the high gain within the SiPM. Now, for the fast output, we would typically use RF-style gain blocks to amplify the fast output. Dan, that's what we've done in our TDC-based reference design. So I guess what was actually done here is that we're operating the TIA front end of the LCA3 as an inverting amplifier. And I think I could pass it over to Rainer now to maybe just explain a bit more about the details of the LCA3.
Exactly. Thank you. It's first of all, for an APD, definitely we need a transimpedance amplifier because the output there is definitely the current. And that's why also, as Aidan said, when we started this project, we definitely focused also first on the standard output because it was the current output. But nevertheless, with using then the TIA as this inverting amplifier, and with the external, let's say, resistor then connecting it to the fast output, we could figure out definitely the advantages of increasing also the pulse width, to make it compatible to the sampling frequency of the ADC. And in addition, with this architecture, you are also able to simple adjust on the dynamic range, depending on how many SPADs per pixel you are using. So, for example, now currently these are in the range of 380 SPADs per pixel with the array we worked with on Semi. But for example, for a different application, there are different number of SPADs per pixel. Then simple, you only have to adjust at the end the external resistor, and from dynamic range, it's then completely, let's say, compatible again. This is also a big advantage.
Okay, thank you guys for that one. Another one for Aidan and Rainer. Cost per channel of $1.20 was quoted. Does this include SiPM biasing in ASIC or just the ASIC? I believe it was just a readout portion, but please clarify that.
Yeah, I believe that's just the readout portion. So I think we saw that the discrete readout, both from a TDC based design and for the ADC-based design, that discrete readout was probably costing on the order of $4 per channel. And then when you move to an integrated solution, I think, Rainer, it's down to maybe $1 per channel.
Exactly.
But that's just including the from the SiPM output to including the amplification and some of the discrimination, because I think, Rainer, on the LCA3, you also have the ADC integrated within that chip, right?
Exactly, the ADCs are in, and then also some kind of digital pre-processing is included. And this was compared at the end to the discrete solution, where we have then for this part the 70% per channel cost reduction.
Yeah, and the other thing to note on this question is, of course, using an integrated silicon photomultiplier array that has the 16 channels on one piece of silicon in a package is also going to be lower cost than having individual detectors for each channel. So that's relevant as well, but we didn't factor that into the cost per channel calculation. That was just on the readout. Okay, so we have about 5 more minutes. So I'll try to get through as many questions as we have left as possible. If we don't get to your question, we can follow up by email for sure. Next one is for Aidan. When it comes to SiPMs, how does it behave with crosstalk and saturation? Maybe this is a good time, Aidan, to explain the concept of crosstalk with respect to an SiPM, and also saturation and dynamic range and recovery time.
Yeah, sure. So the SiPM, it's an array of SPADs, or they're all connected together in parallel. So the SiPM will have a linear output up to about 70% of its dynamic range. After that, it gets into kind of the saturation phase. So in a LiDAR system, if you're saturating the SiPM, due to a high reflectivity target, I guess it doesn't really matter, because you're still going to get the rising edge of the signal. You're still going to get the signal pulse. But when the SiPM is completely saturated, you are at the mercy of the recovery time. So the recovery time is when the SiPM fires, it drops the current that's produced is burnt across the quench resistor. That drops the applied voltage across the SiPM from the bias voltage, which is made up of the breakdown voltage and the over voltage, back to the breakdown voltage. So it drops the voltage and it recharges back up to the bias supply. During this time, the SiPM, it's still if it's completely saturated, all the microcells will have to recharge. During this time, the gain and the PDE are reduced as the proportional to the amount of time, or the amount of voltage that's recharged back on each SPAD. So they're still able to fire, but the PDE and gain are much lower until it's completely recharged back up to its bias voltage. If the SiPM is not saturated, you can have a certain number of microcells triggering, and they'll have to go through their recovery phase. But if other SiPMs haven't fired, they are still available to fire if there's another photon return.
Thanks, Aidan.
And then just on the crosstalk, I guess crosstalk is a phenomenon where you can have a certain number of microcells triggering due to photons generated within the SiPM itself. We do provide a spec on that. So when we put a data sheet out with a set photon detection efficiency, say 18%, we will always spec a minimum crosstalk of say 25%. So you have an idea of what that so the crosstalk, the PDE, and the dark noise are all controlled by the bias voltage of the SiPM.
Thanks, Aidan. I think we're just going to be on the last couple of questions because we have about a minute left. So I will quickly answer these, and we can expand by email. How do these products compare to the single module $3 products like ST Flight Sensor? Just briefly, just to explain, we're showing you a solution that's optimized to work in automotive use cases for long range with 100,000 lux, as opposed to these very short range industrial sensor solutions that you may see. And we can follow up with a more detailed answer on that one. And then another question to very quickly talk about is, how does driving the scanning mechanism work with your solution? So as mentioned, the reference design did not cover the scanning or beam steering portion of the LiDAR system, but the reference design can be leveraged in part and in whole. What we showed is a linear output of 16 channels, which can then be used with a one-dimensional scanning system to drive across the scene, or with a two-dimensional system if you'd like to take those 16 points, scan them vertically as well as horizontally. So we're showing you 16 single points with this reference design. So we're right at 10 o'clock Pacific time. I'd like to thank everybody for attending and asking the engaging questions. The slides are made available now, and we will also be following up with the recording of this webinar. And for any unanswered questions, I would like to encourage you to reach out by email, and we'll also follow up. Thank you for attending, and have a wonderful day.